I would like to move to our next panel discussion right away, where we have challenges for hydrogen-based economy in focus, and where we will look at overview of ongoing research in the field of storage and transport, particularly. And now I would like to introduce the panelists that we have here. I see some of them have joined, and slowly I think they would be here on video. Yes, I see Dr. Lele, I see Dr. Heinrichs, and also Professor Peters. I'm just waiting for a second for the moderator also to be here. And then soon as I have it, then I will make a short introduction to everybody. But maybe firstly, hello to Dr. Lele, Dr. Heinrich, and Professor Peters. Thank you very much for taking out time here. Perhaps I could start with the introductions, and soon as we have the moderator, Dr. Sangwai, we could begin with the session. So I can start here with Dr. Ralf Peters. Professor Dr. Peters is the acting director of the Institute of Energy and Climate Research since October 2019, and professor of energy process engineering at the Aachen University of Applied Sciences. The research group, the institute is called shortly IEK14, as you might find on the website. His work, among others, is on processing concepts and models for sustainable energy systems of the future using fuel cells, electrolysis, and fuel synthesis. Then we have Dr. Ashish Lele here, who's the director of the National Chemical Laboratory, and his research interests are alternative energy systems with particular focus on green hydrogen, on hydrogen ecosystem, new manufacturing paradigm, sustainability, climate change, circular economy, advanced materials, and so on. He has been involved in many strategic science and technology work in India, and particularly he has made the roadmap for the hydrogen value chain. So thank you very much, Professor Peters and Dr. Lele, for being here. Next, I would move on to Dr. Heidi Heinrichs, who heads the group Energy Potentials and Supply Pathways within the Institute of Techno-economic Systems Analysis at the Forschungszentrum Jülich in Germany. Her research and teaching focuses on energy scenarios, modeling pathways towards sustainable energy systems, and integrating the social, economic aspects and technical dimensions of energy systems analysis. She has a special focus on global scale and green hydrogen, and currently leads the Institute's team for a larger project in Western Southern Africa. I see Professor Jitendra Sangwai here, who is going to chair the session here. Professor Sangwai is currently a professor in the Department of Chemical Engineering at the Indian Institute of Technology in Madras, in Chennai here in India, and has over 18 years of experience in academia and industry. His expertise is in energy and environmental engineering, carbon capture and sequestration, nanotechnology, oil and gas, and he has many distinguished awards and research papers to his credit. And with this, I would like to hand over to you, Professor Sangwai, for the moderation of the session. Over to you. Thank you.
Okay, thank you, Adishri, and thank you, Dad and Cards, for inviting me to chair this session. And I welcome all the panelists, Professor Heidi Heinrichs, Professor Peters, and Dr. Ashish Lele for this session. And it's my privilege to be, here and moderate this particular session. And I also like to thank my friend Sachin Gunthe, who had asked me to, moderate this session particularly, and this is how I'm here. So today we are actually going to discuss about hydrogen-based economy and what are the challenges, specifically for storage and transport. So we had initially a lecture, and what we have seen is that how the green hydrogen is important, not only as a source of energy, but also a way to look at, improving our climate issues, particularly by means of, mitigating the impact on climate by reducing the carbon footprint. And as we have seen that there are different forms of hydrogen that comes in, particularly which are being produced from the fossil fuel, without CCUS, which have been produced from fossil fuel with CCUS, and which are being produced from electrolysis by splitting water using renewable energy. And that is how we particularly name these hydrogen based on how they are being produced. So they comes primarily on gray, blue, and green hydrogen. Now, of course, there is a long way to go. And what I was looking at is that currently we produce about 0.03% of hydrogen specifically from electrolysis. That is what is data that is available in 2020. And of course, in the long run, if you see that green hydrogen certainly can take a front seat, specifically looking at how the technology is in evolving in recent times. A lot of focus is being made specifically to understand how the renewable energy sources can be utilized to split water effectively and transport hydrogen in the form of ammonia and different means. So with this, I invite all the panelists to present their work. In a couple of slides, maybe give us some preamble of the focus of the today's talk. Challenges for hydrogen-based economy, storage and transport. So with this, I invite Professor Peters to provide some brief idea about his perspective on the topic, and then we'll go ahead with next panelist, and then this will be followed by question and answer session. Thank you so much. So
Okay.
Professor.
Yeah, thank you for the nice introduction. I try to share my my screen. Okay. So I hope everyone can see it. So today I'm here in this discussion, this panel discussion, with my with another function I have. I also in the steering committee of a joint cooperation between the University of Aachen and the Research Center Jülich. That's the hydrogen cluster. We have gained this project in an initiative which is called Clusters for Future, where we look on several future technologies in Germany, from information side, also to biotechnology, and also to hydrogen. So what's about this cluster? I would explain it very shortly and give you only a brief overview of some of the project. What's the vision? The vision is we would like to have a CO2 neutral and economical operation, and we have to tackle key challenges in this cluster. So we have to overcome low TRLs, so low technical readiness levels. We have to reduce material and production costs. That's from the technology of electrolysis, so of hydrogen production. And we have also to do that in several countries, not only in Germany, also to do that, for example, in India. We have to increase the lifetime and the efficiency, also to do it to generate and also for transportation. We have to create additional incentives so that we can overcome the hurdles of high investments into the infrastructure, and we have to create social acceptance. And we do that in several fields. We take care about the generation, as I explained, about the storage and the transportation, which is the main focus of this workshop today, and distribution. And also we look in industrial use, so not only in hydrogen itself, also in power-to-X processes, we call it. So where we look on fuels and chemicals, and we make here a coupling between the different sectors. So one main thing is, if we look on these TRL levels, I mentioned them before, with 2 or 3, we are in the basic research. And if we are at 8 and 9, we are really near to the market introduction. So we make here a technical development. But we have here what we call a valley of death in immediate technical readiness level. And with this cluster, we would like to overcome this. So what is the basic and what is the strange? We have here several equipment in Aachen and also in Jülich. There's a center for mobile propulsions with a lot of shares at the university. They take care about fuel cell systems and also hydrogen combustion systems. We in Jülich we have a strong material side. Olivier Guillon have explained that just before. We have also in our institute production processes for cell and stack components, assembly robots, and fuel cell testing center. And along these bubbles here, you see also a lot of other things which are also implemented also in Jülich and in Aachen. So at the end, we have 6 institutes in the steering committee, but we have 24 institutes at the university and also in the research center. We have several actors in a local state, which is North Rhine-Westphalia. And we have additional actors also in Germany. So the main story from this cluster is that we start on a regional level and then we make an outcome to Germany and also to Europe and then worldwide. So this technology we developed here would be also available afterwards all over the world so that we can here come to a hydrogen economy. So what is the approach? We have inside of these fields I mentioned before several projects. So some P1, for example, is an electrolyzer. We have also take for the generation production in electrochemical cells. So working with electricity but producing something else like peroxide, water peroxide. We take care about the use and transport, so using hydrogen in fuel cells or in combustion engines. For distribution, we have here a project also for hybrid separation. If we use the natural gas pipelines and take hydrogen afterwards out of the process, the chemical industry, and also some other applications like here high temperature fuel cell for flexible fuel use as a house heating system. So in overall, we have this project P11. I will explain it very shortly, directly afterwards. So for the electrolyzers, we are interested in stability, so corrosion stability tests, and a lot in control. So modeling the PEM and then find a way to work with this PEM electrolyzer in a dynamic system and to control that. For the high-inno nets, so each of these projects are called high-inno, and here the approach is to make fiber and reinforced plastics for pipelines and also to work on hydrogen permeation barriers and coatings. That is also a technical issue to reach here new pipelines. What is also important are tanks. So we have to store the hydrogen. We can do that in liquid form, we can do it in gaseous form, and also in organic carriers. This part here makes sense for smaller tanks, and here these were developed within this project and further investigated. For example, what is very important is the sensor testing to check the quality of the tank and if it's still working in the right way. For this project here, we looked for high-inno PEM. We look on also control strategies and also in measurement of fuel cells and degradation models. We have also a project for combustion here together with Ford, where a hydrogen engine is tested to look also on this side of hydrogen usage. For the high-inno cells, here we work on additive layer manufacturing and also on electrochemical testing and on coatings. Here also the EEK1, as mentioned before, from the material side is implemented because it's very important if we have new materials to invest in tight coatings, that we have electrochemical properties and also we have avoid corrosion effects. And finally then on these levels, we look as an umbrella across all of these projects on the ecological, on a society and corporate level, and on a future level. And that is what I said before. We start on a very local level, then go to the local state, North Rhine-Westphalia, and then to Germany, to Europe, and so on. And we see that here, this hydrogen cluster as a blueprint. And if you further questions, these are the people who are in the steering committee, and you can address every one of them, or you can go to Mr. Sterlepper, who is the manager as a coordinator of these activities. So thank you for your attention, and that was just an impulse that you understand what we are doing here in this project.
Yeah, thank you so much, Professor Peters. Maybe I think we can go ahead with another speaker, Professor Lele, and then we can have questions together from the panelist, from the audience as well. So I invite Professor Lele.
Thank you, Jitendra. I will begin by sharing my slides. Give me a minute. I was not sure exactly what is supposed to be given in the first 5 minutes of presentation. So what I've done is a little bit about what the CSIR program on hydrogen technology is, and maybe a quick overview on the storage and transportation choices that one have insofar as hydrogen is concerned. So for those who are attending from Germany, CSIR is a large collection of laboratories focused on research and technology development. We're not a university, we are a national laboratory. NCL is part of the CSIR chain of laboratories. We are located in the city of Pune on the western part of India. So across CSIR, we have a large program on development of hydrogen technologies across the 3 parts of the hydrogen value chain, which is the generation, the storage, and the utilization of hydrogen. The way we have structured this program is it's a stage gate approach. We have a large number of projects which are sort of blue sky research. We're looking at difficult problems to solve. These are little long-term programs, about 5 years at a minimum. Some of those ideas mature to a point where they pass the first gate and they get into the translational activities. These are what we call grand challenge projects. So few of the blue sky research programs come in there, and the idea there is to scale things up. So convert from the proof of concept to a little higher level. So as the earlier speaker was talking about the valleys of death in the TRL ladder, we are trying to get to the next level of TRLs that is going beyond the proof of concept. There's another gate where if they pass through the gate, they go into what we call mission mode projects, which are very focused to delivering either a product or a process technology. The first two are more focused on generating IP and knowledge. The largest resources are dedicated to the mission mode programs. So the entire program across CSIR has 18 laboratories which are working together. So you may call it a virtual cluster of laboratories working on hydrogen technologies. In the Indian rupees, this is a 100 crore program, and that's about a billion Indian rupees program. The programs are structured so that there are deep partnerships with Indian industry. We are looking at developing globally benchmark technologies, and those technologies where we have already made some progress, we continue to do innovation so that they remain competitive. More importantly, we are also leveraging these small and medium scale enterprises in India who today do not know much about hydrogen technologies, but have the capacity and the resources available to manufacture things that are required for hydrogen technologies. So, for example, developing enterprises for making bipolar plates or catalysts or filament winding of cylinders and so on and so forth. So we work very closely with these small scale industries to leverage their expertise and their resources and bring them into the hydrogen ecosystem. One of the key focus of the program is to develop the core technologies that are required for making hydrogen or utilizing hydrogen. So things like membranes, catalysts, porous transport layers, carbon fibers, composites. So these are core technologies on the basis of which the whole hydrogen technologies are developed. So one of the main focuses of our work is to look at development of these process technologies which are important for hydrogen value chains. We are also involved in helping the various ministries of the government or sometimes even in industry to develop their strategies and roadmaps for the hydrogen value chain. We conduct skill development programs. To some extent, not much today, but we increasingly want to develop, to participate in the development of standards and codes, which are harmonized with the international standards and codes. And we are right now creating some larger facilities, either at NCL or in other labs, or many times in collaboration with other institutes. These are national testing facilities where our technologies as well as other technologies can be tested as per international norms. So this would even require development of testing facilities which are able to do the kind of testing that is necessary for certification. So these are the various activities that we do at the CSIR laboratories. Some of our successes are shown here. We have created testing platforms for fuel cells and electrolyzers. We have developed the first Indian fuel cell cars and buses, also stationary power backup systems. We have a small pilot plant to make steel, purely green steel from using hydrogen plasma. We have developed both PEM and SOFC electrolyzers, and we also have a coal gasification pilot plant, which also produces considerable amounts of hydrogen, although this is right now gray hydrogen because we do not have the ability in this pilot plant to also sequester CO2. We do capture it, but we don't sequester it as of now. This is our first indigenous hydrogen fuel cell bus. This was launched late last year. And everything here is purely indigenously developed and also manufactured. Okay, so that was a little bit about the hydrogen program in CSIR. Jitendra, is it required to give a short overview on hydrogen storage and transportation, or should we do this as a panel discussion?
Yeah, you can give it right now, and then we can have a question and answer then followed by. Okay.
So maybe a few slides on my take on storage and transportation. There are, of course, various options available for hydrogen storage, and these are given in the left-hand chart, which talks about the gravimetric and volumetric storage capacities, ranging from very low gravimetric and low volumetric to reasonable gravimetric and volumetric capacity. So multiple options are available, but it's not just about storage capacity. It's also about the energetics required to extract the hydrogen from the stored container. So again, on the left-hand side of this dial, we have materials that can store large amount of hydrogen, but also require large energy to extract the hydrogen from the material. On the right-hand side, we have materials that have much less energy requirement to extract hydrogen, but also lower hydrogen storage capacity. So it is those materials that are at the center of this dial, which look interesting, which have reasonable storage capacity, as well as the requirement for energy is not too high as well. So these are the kind of materials which are today considered very interesting. Three types of hydrogen storage are in very generic terms are solid state storage, liquid state storage, and gaseous. Of these, the gaseous storage is typically in the form of compressed hydrogen gas. This is perhaps the most well-used and highest TRL technology with reasonable gravimetric capacities, is widely used for a variety of applications, pressures ranging from 350 bar all the way to 1100 bar. But if you do a sort of TCO analysis specifically in the Indian domain, we think that something like 500 bar would be the most optimal for us in India. There is, of course, a carbon fiber target cost. Today, about $25 a kg has to come down to below $10 a kg in India. Something like $6.5–7 a kg is what is required to make this viable. there is a safety perception, of course, for these cylinders because of the very high pressures. And the other concern which we in CSIR are today working on is the sustainability part of this, because although the life of these cylinders is about 20-25 years, at the end of life, we don't want landfills to be filled with used and end-of-life hydrogen cylinders. So we are looking at new technologies by which the hydrogen cylinders at their end of life can be recycled completely. This also has implications on the capex of these cylinders. The second is the liquid organic hydrogen carriers. The ones that are currently being pursued are materials like toluene and dibenzyl toluene. They're at reasonable TRL levels. There are companies around in the world who manufacture them and use them. Supply chains have been demonstrated across continents. They have reasonable gravimetric storage capacity. However, their biggest problem today is the large dehydrogenation energy required, and that makes their viability a little bit of a concern. They also have a little concern on cyclability, especially those LOHCs that are that have other than carbon and hydrogen atoms in them. They had heteroatom LOHCs have some issues with cyclability and durability. The third is the solid parts, which is the metal hydrides. These do have both higher volumetric and gravimetric capacity, and so they're quite attractive. However, there are issues with them with regards to cyclability and creation of dendrites and so on. But also important is their safety, because these are very pyrophoric materials. So they also have the problem of large energy required for desorption of the hydrogen. So the ones that are today most interesting are the what are called the high entropy alloys, or to some extent also a few MOFs. So these are the lowest TRL levels. There's a lot of science happening behind them. A lot of people are today using AI/ML tools to find out which might be the most optimum high entropy alloys. They're interesting because they have been demonstrated to be easy to couple with both electrolyzers and fuel cells. Their cyclability is right now a little bit of concern, and the gravimetric capacity is well below things like compressed hydrogen or the LOHCs. There are other systems such as ammonia borane and so on, but I don't think I should spend much time on it right now. Coming to transportation, we have, of course, the road or rail kind of transportation on land, shipping between continents. And of course, if you are transporting very large amounts over long distances, eventually pipelines become the most desirable thing. I think marine transportation is picking up in a big way. And in the recent COP27, many organizations have signed a piece of paper that where they commit to rapid and ambitious production of low carbon fuels for marine transportation. And this is driven by the fact that the greenhouse gas emissions of these sectors are very significantly increasing today. So in marine, people are looking at various types of options, from ammonia to hydrogen and everything in between. I think the jury is not out yet as to which one would be the most optimal one. But I don't think it's ever going to be that way, because depending on what is available where locally, the choices for these various fuels will be made. What is clear is that the shipping industry will definitely move to various types of green fuels. For long distance transportations on land, it is the pipelines, which eventually should come up in a big way. Today, we have two types of solutions available. Either there are tube trailers, or there are, so these are mobile pipes as they call it, or there are flexible composite pipes which can be laid across the ground, and there are wonderful technologies available for this. However, these are meant right now for lower volume transportation, but over longer distances. Of course, Europe, friends in this call will know much more about it than I do. The European Hydrogen Backbone project seems to be the most exciting one in terms of pipelines, with more than 10,000 kilometers of pipelines across the countries on the continent being planned. So it's probably the most ambitious one on pipeline transport. But in India, we are looking more of decentralized production of hydrogen. India has sort of now declared about 10 states where which are most amenable for hydrogen production. And if you put various things on this map, along with the states where hydrogen production will be done, you will see that decentralized production of hydrogen where the offtake is required would be the most optimal way for transporting hydrogen. Leveraging local resources and supply chains is also useful in reducing the hurdles for storage and transportation. We are looking at avoiding more than 200 round-trip kilometers for transportation because of the prohibitive cost for storage and transportation. And sometimes we discover that transporting molecules perhaps is more viable than transporting electrons, which is a little counterintuitive. But this again depends on the use case. The other thing is the digitalization framework in India. The infrastructure for digital systems in India is very robust, is very economical today. We have the lowest cost data available across the world today. And India plans to have a large national logistics policy, which in principle, along with which is built on the digitalization platform. And I think green fuels like hydrogen can benefit immensely from such kind of national initiatives. So with that, I will stop here and will be, of course, happy to answer more questions. Thank you very much.
Thank you, Ashish, for wonderful information about hydrogen storage and the development that has been done at CSIR. So, yeah, we'll have questions after we have, presentation from Dr. Heidi Heinrichs. So I welcome Dr. Heidi Heinrichs with a request to present.
I hope you can see my slides by now.
Yes, we can see your slides.
Perfect. Thank you very much. So you will see one or some of the slides you might have recognized before by my colleague when it comes to scenarios, because the main topic of our institute is dealing with systems analysis, but I will go into that detail a bit more. So who we are, so I come from the Institute of Techno-economic Systems Analysis, and our core aim is to provide action knowledge with systems analysis, so provide information that then can form the basis for decision support. This we do in a big team, so currently we're around 40 to 50 people working together, highly interdisciplinary to bring all the aspects that are relevant together. And I just have put here some exemplary project which we did or are currently doing in that area, but I guess those slides will be shared later so that you can have a look at that as well. How we are doing this, for this, all of the analysis we do, we apply our so-called ATOS model suite, which brings together model modules from different sectors and areas, and we combine them in accordance to specific research question we want to answer. Today, the focus or the tools we have applied for the results I will show are centered around our energy system model in the middle, and we have used tools for renewable energy sources, hydrogen infrastructure, and exchange of hydrogen on a global level. So maybe starting with why we have looked into hydrogen at all, and especially in green hydrogen. Ralf Peters have already mentioned it, that in Germany there's the need, or it's foreseen that hydrogen will play a crucial role when we aim for greenhouse gas neutral energy systems. And you see here the expected increase in hydrogen demand based on analysis we did in that regard. And roughly half of this is expected to be imported to Germany. So even if we assume green hydrogen here, it seems to be that Germany will still remain being an energy importer. And then the question arises, from where can we get those? That will be a part of the slides I will show afterwards. But why is it that green hydrogen can play this crucial role? For this, we have done, for example, an analysis over full Europe in terms of renewables, and see how would, so is it possible maybe if we look at Europe as a whole unit or region, that weather condition can match each other in a way that we do not need too much storage. But the result showed that you can see here in the diagram that that's not the case. So there's an effect that we can balance over Europe, yes, but in the end, there's still a lot of need for storage, especially on seasonal level. And for that, green hydrogen is a big option for sure, especially when it's combined with salt caverns. So that's an option for underground storing of hydrogen, which is quite cheap. And we have done an analysis for Europe where you can place hydrogen salt cavern storage. And especially Germany has a big potential there. So currently we are working on an analysis to do this on a global scale. So maybe that might be interest for the Indian colleagues as well. Another aspect we have to consider there when we scale or design energy systems is the impact of weather years. Because normally, sorry, when you look at scenarios, you often have the thing that it's designed for one specific weather year. But we have investigated how system design can change if you consider different weather years. So it's very sensitive. You have some base trends, but especially when it comes to biomass, for example, there are years there's no biomass at all in the system we have analyzed here, while others where biomass play a big role. So whenever you design, let's say, strategies or scenarios for a country or region, you have to consider impacts of different weather years. And when we look into the future, climate change should also be considered, as weather patterns can change over that time as well. What we also consider when we analyze scenarios is always the potential synergies and competition for land and energy resources in the areas where we look at. For this, we normally have a full land eligibility analysis where we look, okay, where can we place renewables and where not? And in this regard, we are always interested in, let's say, local perspectives, because we can do that on a global scale, and we have done similar analysis for India as well. But that's mostly, let's say, default values on a global scale, but having local perspectives, so what's the preferences of the people living there is much value to refine those approaches. Based on that, we typically do simulations of wind turbines and photovoltaic modules combined with weather data. And then we design a hydrogen infrastructure, how we could, for example, in this case, this Patagonia is shown in South America. Where can we connect wind parks together to electrolysis, and then connect the electrolysis with hydrogen pipelines to a potential exporting harbor. And in the exporting harbor, we then can derive export cost independence of the capacity expansion, we assume. Crucial here is that this required land for hydrogen infrastructure should not affect the well-being and the economic development of the local population, because normally you look at, let's say, a static land use, but land use is dynamic, so this should be considered as well. Then, and that's the good news, normally in a lot of countries globally, there's a lot of potential for renewable energies. And one can think about which, let's say, synergies can be identified for infrastructure development, for hydrogen export, but also to improve local energy infrastructure, for example. And another thing is, especially for PV-rich regions or sun-rich regions, so that the if you look at the expansion rate of so photovoltaics there, then in cost is quite stable, because the deviations in solar radiation in those sun-rich region is limited. meaning that there is only low competition for best locations. That's different when we talk about wind energy, because there the deviations are much higher and there could be competition. So when it comes to, do we use the renewables for, let's say, hydrogen or for electricity, etc. But then there should be a balance. But this competition is only low for photovoltaics. Another thing that has to be considered when we talk about electrolysis is the water demand, for sure, especially when, as I mentioned before, when we talk about sun-rich regions, but not only those regions, because, for example, also Germany has an issue with water stress, even if it's now quite wet outside. And we have started looking at maybe selecting 25 just exemplary renewable-rich regions which have coastal access to analyze which exchange could happen. And if you then look on the water scarcity in that areas, you see that most of them have an issue in that regard. And in literature, normally it's expected that the water scarcity starting from 40% is something like where no sustainable water use is possible anymore. For those regions which already have water scarcity even without climate change, seawater desalination could be an option, because when you compare cost for seawater desalination, it's very, very low compared to expected levelized cost of hydrogen. But for sure, we have to be careful in that regard, because it really depends on how you design the seawater desalination plant, if it's sustainable or not. So if it would impact the marine life or not. That's especially dependent on how you design the outlet, because you use a lot of water going through the seawater desalination, and a brine is coming out, and how that is bringing or brought back to the sea, and how this dilute. So it has to be sure that it does not impact local marine life there. That's possible, but therefore we will need regulations, because it's a bit more expensive to do this in a sustainable way than just doing it. So I fear if we do not regulate this, we will see a lot of impact on sea life. But on the other side, if we would just aim for local water, we might even have bigger issues in terms of that there's not enough water for population, for drinking needs or agriculture, etc. Sorry. So another example, or what I've brought to you today, is something we have done for West Africa, where we have created a green hydrogen atlas. There's also, you see in the link below, there's an online GUI where you can explore the results we have published so far. And there again, we started with looking at where we can place renewables in exchange with our local partners. Then simulate, in this example, the wind generation and derive from that local green hydrogen potentials, and then combine that with sustainable groundwater availability there. And you can see here in the blue text that roughly only 35% of the technical potential remains if we limit it only to sustainable groundwater. Hence, the role of seawater desalination became even more obvious. What you see here, what we did for West Africa, we could potentially do for India as well. So if any one of you might be interested in something like that, please contact me. Maybe we can explore some options how to do something like that together, especially maybe to exchange about what the preferences of India are in those regards. When we bring all of that together and look, okay, how could a potential pattern look like? Again, here only with some exemplary regions globally, then we can see that the very long transport let's say, between the bigger continents is not part of a cost minimal solution. But cost minimal is only one aspect of trade for sure, because security of, or that's the reliability of the partners is something that come into play there as well. But if you only look at cost here, then we can see that the maximum transport distance is around 12,000 kilometers. And here we have assumed the liquid hydrogen as an exchange carrier, because when we analyze different transport costs over the future, we see that there's the biggest option to have the cheapest transport option when it's come to those big distances. And we have focused on ship transport because we think that that can lead to a more let's say, free market without a lot of market power or concentration on only some trade flows, because as soon as you have pipelines, you're directly connected to your supplier, and Europe is currently facing the uncertainty that is related to such constellations. So here we have analyzed the ship exchange. The challenge here is that we talk about shipping hydrogen around the world, is that currently the transport of the ships itself is not as green as we wanted. So there's still research needed to have green hydrogen driven ships, for example. There's ongoing research for that, but it's not available on the market by now, but I hope that it will come soon. We have just estimated maybe for this specific scenario how much ships we would need. So it's roughly 1,000 ships until 2050. And that for sure leads to the question, do we have enough marine infrastructure to build those ships? Which is quite interesting, because when you look at what's currently there, you can see, and that's one of the reasons why a lot of people talking about green ammonia, because there are ships in theory available running around the world seas. The challenge there is that if, let's say, the global north now starts to think about shipping green ammonia as a hydrogen carrier, there might be doubt that enough new ships can be built, and those ships then ordered by the global north might be missing for fertilizer production, which then can have severe impact on food production on global scale. So there's a singles where we see shipping green ammonia in terms of food security on a global scale quite critical. But nonetheless, we will need a ramp of marine infrastructure. And Kawasaki have already started to gain experience with a hydrogen vessel, and we hope that they will proceed there as well. Here, maybe I can just go shortly over it. You will get it in the slides afterwards, I guess. When you consider hydrogen on a global scale, there's a lot of countries who could enter the markets, and that can lead to relative stable costs when it comes to imports. So it could be different compared to, let's say, the fossil markets by now. And I think that's a big challenge for the world. Maybe to sum up, so the key takeaway messages, when we aim for climate neutrality, then green hydrogen is a clear pillar for that pathway. We should be aware of creating or being aware of synergies and competitions when it comes to resources, especially in land and energy. We should have seawater desalination included in the strategies, but please be aware that it's designed in a sustainable way. When it comes to transport, distances are in a way limited. So in our case, it was 12,000 kilometers at the maximum, and green transport option on a global scale would be required. And we hope at least that when we have a lot of different export countries, that there will be a really free market, so that their market power is not concentrated only on a few countries.
Okay, I think.
Thank you very much. And I have some links here, so if you're interested in some projects, please feel free to have a look at that later.
Yeah. So thank you so much, Dr. Heidi Heinrichs, for a nice insights into the hydrogen storage and transportation in Germany. So now the session is open. Now we'll have some questions from the audience. I think there are already few questions that have been there. And I request audience to drop a question specifically for any speaker that you may have in mind. So there is a question by Dr. Sumit Agrawal. I think anyone can answer this. Particularly, I want to take this question to Professor Lele. How do you see the state of the art of electrolyzer manufacturing in India, such as PEM or SOEC?
Right now, there is no real manufacturing happening. There is a company in our city of Pune which has actually licensed the technology from Germany, and their intention is to manufacture SOECs and SOFCs. Okay, so that is the intention, but the manufacturing will take some time to get started. I think right now several companies are looking at setting up demo experiments to look at various electrolyzer technologies in their own plants and to check how these various electrolyzer technologies perform, compare them for the Indian conditions. And that is the activity right now going on. So I think it's a little long way to look at commercial manufacturing of electrolyzers.
Okay, thank you so much. I think there is another question. What is the highest capacity plant installed in Germany or global as far as green hydrogen is concerned? I think Professor Peters can answer this question. I think we cannot hear you. You need to unmute yourself.
So yeah, I can try it, but I think also Heidi Heinrich can do that very good because you have a good overview. So if we have in Germany something like 500 to 600 terawatt hours electricity, and if we go in the future, we have a much higher electricity demand, and then we need also something in the gigawatt range on electricity electrolyzers. So there are several forecasts concerning that and several models, and it depends how much is the hydrogen economy will be extended. But we have in this in a number in several gigawatt range.
Oh, okay. So there is another question by Mr. Rohit Narayanan Srivastava. Maybe Dr. Lele can answer this. How do you see the role of electroplating and coating industry in manufacturing and development of an electrolyzers?
Very interesting question. I think this is I think it's very required because corrosion is an issue in electrolyzers, especially PEM electrolyzers or even the new AEM electrolyzers, or even the end plates of alkaline electrolyzers, and so all of these, because of these strong either acidic or alkaline conditions, the various parts of the electrolyzers need to be protected from corrosion. Electroplating is a large industry in India and a very robust industry in India. So the infrastructure is available, the expertise is available, there is capacity there. It just has to be used, and for the purposes for electrolysis. And in fact, this is one of the things that we are doing. We're working with two local electroplating companies to see if they can sort of understand what is required for making corrosion resistant plates, or even end plates, fittings, and many things like that. So interesting question, and I think required. There are, of course, companies in India who make the materials required for electroplating, the right composition of materials required for electroplating. So the materials are there, the electrolytic baths are there, companies are available. This is the kind of infrastructure that one can leverage very quickly to start the manufacturing of these components. Yeah.
Just in continuation with that, what is the economics? The question by Sanjay Singh asking about economics of electrolyzer technology specifically.
Maybe the German guests on the call can answer that, because there are
Yes.
many numbers floating around and it's all driven with scale and so on. So can I pass it on to the other experts on the panel?
Yeah. Heidi, Heinrichs, you have anything to say about it?
Yeah, so it depends on which electrolysis technology you look at. And some of them, as was presented before, especially by our colleague Oliver, is still in research. So when you want to buy something now, the easiest way is to aim for AEL. But there's strong options for PEM as well. But before I talk into details here, we have the perfect expert in that regard, which is Ralf Peters, because he's part of an institute who really do electrolysis research. So maybe he can add more perspective on that, because he's the real expert there.
Yeah, if you go now to buy one, that's right. You go for an alkaline one. You can buy them from different suppliers worldwide. You have to pay the price from today, so you get an offer for them. If we look on the future costs, we calculate with investment cost of 500 euro per kilowatt. But this is not the reality today. From the technology side, I think we have always a competition between PEM electrolyzers and alkaline ones. So the PEM electrolyzers hurry up along and have perhaps a better dynamics, also a better issues in regard to the gas qualities. But that's something each one have to see also in his applications. And finally, I see also that we have a chance with the high temperature SOFC in the future. But I think, and we have also the possibility to match the advantages of PEM and alkaline technology. But that's really on the beginning. So from the technological side and from the research side, we have a lot of opportunities to improve that. But today, I would say alkaline and PEM are the first who will be introduced.
Okay. Yeah, there is one more question by Prerna Yogeshwar asking about the material. What is the material that is used for the vessels, and how does it address the challenges of hydrogen seeping through? I mean, it is open to all panelists, whoever can answer this question.
Vessels, we didn't understand exactly what
material that vessel, the storage, particularly with respect to the storage, I think hydrogen storage. Asking about the material which is used for the hydrogen storage and how does it address the challenges of hydrogen, which might be seeping through in case of leakage or something. That's what I understand. I mean, the question is not still clear to me.
Yeah, so for high pressure storage, it has always been carbon fiber composites because we need pressures beyond 300 bar to have meaningful storage. So that's clearly the liners are mostly polyamides. Some companies are also developing polyolefin liners. Polyamides are better because the leakage through the polyamides is lower. The diffusion through the polyamide liner is lower. And the carbon fiber composites are essentially to give strength to the cylinder. But it's also the joint between the hub and the cylinder is also very critical. The liner has to be seamless. The joint between the hub and the composite has to be without any joints. I think those are the more difficult areas in terms of manufacturing. I don't know if that answers the question asked.
So as an engineer, I always wonder that when you talk about this electrolysis using the renewables, why can't we use electricity directly rather than splitting water and again using hydrogen and again converting into electricity later on, doing combustion? So if we are at all using a renewable energy, I can directly use electricity for my end use. So what is actually the need to produce a hydrogen, green hydrogen?
Yeah, maybe I can answer that.
Yes,
Because,
please.
yes, for sure. If there's an option to use electricity directly, that's always the preferred pathway, because then that's more efficient than using the route via hydrogen. But as I have shown before, the volatility, especially of wind energy and photovoltaics, is so high that if we want to have security of supply throughout the year, we need a lot of storage. And storing energy in that amount over, let's say, a seasonal time frame, that's the way, or that's the option or the role of green hydrogen, because that can be stored in a big, so a big amount of it can be stored quite easily, and compared to other storage options, it's quite cheap. When it comes to seasonal storage, I'm not talking about maybe balancing daily patterns or something like that. There are other storage options can play a role as well. But when it comes to seasonal storage, there's a role of green hydrogen, and then it can be used to as maybe having it as for re-electrification in times where we do not have renewables, but it can also be used as an adduct for chemical industry, etc.
Okay, thank you. One more question.
Jitendra, to add on
Yes.
to Heidi's reply, in many use cases, hydrogen is required as a molecule, as a feedstock, and you cannot use electrons there. You can't refine steel with electron. I mean, you can, but those technologies are much lower TRL levels.
Okay.
Yeah, so sometimes hydrogen is required for as a molecule.
Yeah. Right now, the total amount of hydrogen, the blue hydrogen, the green hydrogen is about 0.03% is being produced, and 95% is still being produced from the natural gas, while the majority of it comes from fossil fuel. So how do you see the timeline as far as looking at, say, 90% of hydrogen or say green hydrogen coming out? Open to all panelists, whoever can answer this.
I think that depends a lot of local regulations, policies, etc. So which ramp up in terms of renewable expansion can we achieve? Because without enough renewables, we are not able to increase, let's say, the green hydrogen based on water electrolysis. I think that that's a crucial part there. So there's a lot of announcement that policies aim to become climate neutral by, let's say, 2045 or 2050. But we also see, especially in Germany, the challenges when it comes to really expand renewables, that there might be local barriers, etc. So it all depends on which expansion in terms of renewables we can really achieve.
Yeah. So do you see that the green hydrogen will possibly reduce the use of battery as far as the energy storage and usage is concerned? Because you talk about hydrogen-based fuel cell cars and automobiles in near future. So what do you foresee in that perspective?
I think when it comes to Ralf, please.
Yeah, I think we need both technologies. So if we have electricity and we look on the efficiencies and we have not to store it in the long term, the best way is to use directly a battery electric vehicle. But if we think about heavy duty trucks and local distribution, then fuel cell driven lorry or duty vehicle is also a very good option. And then the fuel cell have a better efficiency as the engine. Sometimes perhaps you use better internal combustion engine, but I think the fuel cells have here a good chance. And so we should not see this as a competition. We should see that electricity-based systems and hydrogen-based systems have both their role, and we have to fulfill this this great challenge. And for that, we need all these technologies.
Yeah, that's great. Yeah, I think with this, I think I can conclude, based on our discussion and based on the insights and the pre-presentation that have been given by all the three panelists and the questions that the green hydrogen technology not only will address the requirement of energy for the mankind. But it also requires a technological innovation and development in near future so that hydrogen production becomes economically feasible using renewables, and then also the technologies with respect to the hydrogen storage and transportation by means of converting it to ammonia or storage in terms of different materials is required, in near future. And with this, I think not only that, it will address the climate change, climate issues, and in fact, there is a lot of interest and from the people that I can see from the audience, and also the India and Germany collaboration can certainly take a way forward. This IIT Madras has been, one of the institute that has been started with the German collaboration. And I, being a dad fellow also, it's really great to be here as a part of this panel. And I look forward improved collaboration between Germany and India with respect to institutes and research collaboration on green hydrogen, and also CSIR with Dr. Lele as a front seat. And thank you so much. And if you have anything to say, maybe we can conclude otherwise. Yeah, Adishri.
Thank you. Thanks a lot, Professor Sangwai. Thanks a lot, Professor Peters, Dr. Heinrich, and Dr. Lele. This was a wonderful session, gave us a great insight into the ongoing work right now and models in India and Germany. We would like to move on to the next session now. If you would, of course, like to send us some links or your presentation to circulate, you're welcome to let us know, and we will send it around next week to the participants. So I would like to say thanks a lot once again. Thanks for taking out the time. We'll stay connected with you.